Okay, so at this point, we've talked about the cell membrane, we've talked about how its structure is designed, and hopefully you have a better idea of phospholipid bilayer and integral proteins and peripheral proteins and even cholesterol, at least what their job is. But that only explains the structure of the membrane. That doesn't explain how materials move through. So that's really what we want to focus on today. So this just continues the notes that you already have. Material transport across a membrane, there's two main methods that we can use, or your cells can use, to move stuff across the membrane. It could be going into the cell, it could be going out of the cell, but either way, it always has to go through a membrane. I guess I gotta be a pen. Okay, so these two major methods, the first one's called passive transport. Now when I see the word passive, I think of someone who doesn't get riled up very easily. All right, so you could pick on them, you can try to get them mad, and they just, I'm not gonna really react. Well, that's being passive. In terms of the cell, we would define this as any method that does not require, or methods that do not require the cell to use up its energy. So these don't require the cell to use up its energy. Now, a cell's energy is in a molecule called ATP. This is what happens with the mitochondria. The whole reason we call it a powerhouse. Glucose comes into the mitochondria. Excuse me. Glucose comes into the mitochondria. It goes through a series of reactions called cellular respiration. And then what gets kicked out are a whole bunch of these. So that's the energy. It's kind of like money. Sometimes we call it the energy. Sometimes called the energy currency, which is kind of like money. All right? In order for you to be able to do anything, you pretty much have to have money. Cells, much the same way. In order to do anything, it has to have ATP. Okay, so these are ways for the cell to move stuff without using energy. Well, its own energy. It does rely on the random motion of molecules, something we call kinetic energy. So kinetic energy is this energy of motion. Even something solid, the particles in it are moving. Now they're not moving much, but they're moving just like a vibration. Sometimes we call it Brownian motion. Okay. Well, let's look at an example of passive transport. This one's called simple diffusion, and it's defined as the movement of molecules down a concentration gradient. And if you're not familiar with that term, a concentration gradient is when you have an area of high concentration on one side of the membrane and an area of low concentration on the other. Okay, for example, if I've got a cell membrane and I've got particle X and particle X, well, there's a difference there. I've got a lot on this side of the membrane, but only a few on the other side of the membrane. That's something called a concentration gradient. And what diffusion says is the molecules move down the gradient. So they're going to move from where there's a lot to where there's not. Okay, so some of these are going to move across the membrane to try to balance it out. Okay, just by random motion. For example, let's say I've got a room with some particles, and these particles are bing, 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 bing. They're bouncing around. I can't move all of them. But as they're moving around, they hit into the walls, they hit into each other, okay? And they're going to spread out in that space. These guys are doing the same thing. They're moving around, they're vibrating. Some of them are just maybe moving just a little bit. And what you end up seeing is they spread out. Now, what if this door, we'll pretend it's a door, could open? What would happen to the particles? Well, some of them, like this guy maybe, he's moving maybe this direction, hits off a wall, hits off a wall, hits into the door, and eventually maybe it goes to this side. But most of them, more are going to go to this side just because there's more of them on that side to begin with. Now, eventually, if you notice, if we let this go long enough, what you'd end up finding is it kind of reaches a balance. Now, this isn't exactly equal. We've got 2, 4, 6 here, and we got 2, 4, 5 here. But at some point, you get what's called equilibrium. Keyword equal. Well, in this case, we may not be able to reach equal exactly, but as these guys are moving around, they will balance out. You won't have that high and low. You'll have it balanced. Okay? Now, could we end up with something like this? Do you think that would ever happen? No. Okay, once you open that door, as those are moving around randomly, you're never going to be able to get them all into one side because there's always going to be some that are moving the opposite direction. And they're going to find that door. Okay, just happen to go through, boing. And eventually you're going to end up with something that is roughly equal. And that's when diffusion stops. Diffusion stops when you no longer have a high concentration. You don't have a high concentration or low concentration. It's just balanced. Okay? Now, something you got to be a little bit careful about. Even though it's at equilibrium, do these molecules ever stop moving? Just because they reach equilibrium does not make them stop moving. Molecules are always moving, even if it's just moving in place. Okay? They're always going to be moving. So even though they're balanced, they're always going to be constantly moving back and forth. It's just moving in a balanced way. All right, hopefully that makes some sense. The next thing we want to talk about is some things that can affect the speed this happens. The size of the particles, large particles, move slower. And I think that kind of makes sense. If I've got a football player that's a center, they're big. They're designed, they're built to get in the way. So they snap the football and then block. They just basically form a wall to try to prevent other people from getting through. For cells, that's stuff like polysaccharides, big sugars. Nucleic acids are big, complex molecules. They don't move very quickly. Now, small Small particles like oxygen and water and even amino acids, these are little guys that are going to move quick, kind of like a tailback. They're small, they're agile, they're able to break tackles and spin, okay? And the difference is pretty striking. These guys weigh a lot more. These guys better not, otherwise they're not going to be able to move. They're not going to be able to move very fast. You don't see centers scoring touchdowns. Okay, so particle size makes a big difference. Big particles move slow. Small particles move fast. Temperature is another one that affects diffusion pretty bad. Okay, so the hotter things are, well, let's put it this way. Colder something is, the slower the particles move. If the particles are moving slower, then diffusion is going to happen slower. Okay. The last one, steepness. Let me show this one a little differently, and then we'll write something down. Box on the left. I've got a lot of particles on one side of the room, very few particles on the other side of the room. Okay? Box on the right, I've got a little bit more on one side than the other. Both of these have a concentration gradient. This is the high, this is the low. Same thing here. But the difference is, this is like a really steep hill. There's a big difference between the top of the hill and the bottom. That's really high and really low. Well, same thing here. There's a lot of things here. That's like the top of the hill. And very few things. That's the bottom of the hill. Here, well, that's kind of like a hill like this. Yeah, there's a difference, but there's not many more than what's here. Okay, so it's kind of like a very shallow hill. Now, I think most of you can figure this out. If I open this door, and I open this door at the same time somehow, which one's going to diffuse faster? Oh yeah. All right, this one's going to be, they're just rip-raring ready to get out of there. And so they're going to diffuse really fast until we reach equilibrium. And maybe I went too far. 2, 4, 6, 8, 9. 2, 4, 6, 8. So there's one that's kind of floating back and forth. Okay. Now, the other one, yeah, they're moving around. They may eventually move that way. They may not be able to get through there. But eventually, they will reach an equilibrium as well, but it may take longer just because there's fewer moving. They both will diffuse, they both will reach equilibrium, but this one will take longer. So, the less of a difference in concentration, the slower. Okay, hopefully that makes sense. Last one. Facilitated diffusion is the same as simple diffusion. So we're going to go from high to low along the gradient. We're going to go from where there's a lot of something to where there's not. But the difference here is we have to use an integral protein. Well, there's only certain molecules that need to. These are going to be polar. Polar stuff, proteins, things with a charge, are going to need to use a special protein to get through the membrane. That's called facilitated diffusion. Now the trick with this is they have to fit the protein. There's going to be a special, it's almost like a lock that has a key. I can't just put any old key into that lock. It has to be a perfect fit. So, if I've got a membrane like this, let me see if I can bring up this animation real quick. Sorry, I didn't have that ready to go. Okay, so imagine we've got something like this. Here's our cell. Here's our phospholipid bilayer right through here. This part's non-polar, so these polar guys, these are all polar molecules. They can't normally go through. But if there is a protein that it fits, it can use this like a secret passageway and go into the cell. Well, right now we've got 1, 2, 3, 4, 5, and inside we only have 1. Well, there's a gradient. This is your high concentration. Here's your low concentration. It is wanting to go through, but if this protein wasn't here, it wouldn't be able to. But because it is there, let's watch and see what happens.
In the process known as facilitated diffusion, a special carrier protein with a central channel acts as a selective corridor which helps molecules move across the membrane. These special carrier molecules that form the protein channel bind only to a specific molecule, such as a particular sugar or amino acid. Once the molecule binds to the carrier protein, this protein helps or facilitates the diffusion process by changing shape and moving the molecule down its concentration gradient through the membrane into the cell where it is released.
Okay, so there you go.